Let's go over the 39th CPhO question 6. This question is probably one of the hardest problem in CPhO 39. And let's read the question first. So the question first stated that there are like two planes over here, which has like charge distribution of sigma minus and sigma plus. And there's no E field outside of the region from x to is equal to negative L and x is equal to L. And the problem is saying that if there is a temperature gradient, there will be like changing the electron number density. Well, the total amount of charges inside the plate should be 0. And let's try this problem, the first question. Let's go. So it's saying that there's like particle number density of nx, and the diffusion gx, which is the particle flow density. Something to notice here is that this one is not the charge flow density. Well, it is the particle flow density. So you need to keep in mind. And the equation is given by the Fick's law over here. And d is equal to this constant. And now let's go over how to solve for the electric field Ex. And so first, we need to use the Ohm's law. Oh wait, I need to add something. Is that at equilibrium, there should be no net current flow, right, inside the metal. So the aforementioned electron diffusion flow is counteracted by the drift current generated by the internal electric field. So that means we will have this equation over here. And using Ohm's law, we can see that the drift current generated by the internal electric field is actually equal to this using Ohm's law. And now let's go over to the electron diffusion rate, which is equal to JE. And something to notice here is that this is the particle flow rate. If we want to like get it into the same unit as the drift current, we'll need to like time this term by negative E, where negative E is basically the charge of the electron, right? So we need these two terms to balance each other out. So now this sigma is equal to 1 divided by rho, and we can reorganize the equation into this form. And now if you just plug in the equation for this, you actually can see Ex is equal to this term. And that is problem 1. Let's move on to question B, which is a harder one. So for this one, you are told to derive Ex using the Gauss theorem. So how do you do this? Is that you only need to consider a small slab where the width is dx and the area is a. And inside this, the area is actually equal to a dx, right? And if you time it by the number density, nx, that is basically the total electron inside this volume. But you need to keep in mind that there's like positive charge background. So that means the positive charge has number density of n0 or n0, right? And using the Gauss law, we can see that Ex plus dx minus Ex times a, where this term is basically the same as this, right? Is equal to the total number charge inside this volume, which is nx, and notice there's a negative sign over here, times e and minus n0 divided by epsilon 0 a dx. And if you reorganize the equation, you will actually get dE dx is equal to this term. And now from 1, we actually know the formula for Ex, which is equal to this term, right? And then we just need to plug into the equation over here, and we will get this ginormous equation. And that is like basically how we solve question B. And we also need to consider the boundary conditions. And we're told that the surface charge density of the right plate is equal to sigma minus, and the right is sigma plus. And using Gauss' law, if we only consider the surface which contains the charge of sigma minus times the area, you can see that because we set the electric field as pointing to the positive x direction, you will get this equation over here. Look at this equation, because like E is pointing outward. And now you only need to plug in the equation, and you'll see the boundary condition for the left side is actually equal to this equation. And now similarly for the right side, you can see that because the electric field is pointing into the surface, so we'll have this equation over here. And this. And we need to keep in mind is that overall the system is neutral. So if we consider a volume over here with area of A, the charge over here is sigma minus A, and this part is sigma plus A. And how about the total charge inside the volume, or the other charges inside the volume? It's not the total. So we will see that the total charge is actually equal to nx minus n0 times negative e dx and times a, and you take the integral from negative L to L. That is the total amount of charge. That is not the total, but that is like the other charges inside the volume. So you also need to set it to 0. And that's problem B. Let's move on to the hardest part, which is question C and D. So it is asking us to linearize the equation in B, which is this part. So it is saying that we only keep the terms of the delta n and delta t, while ignoring the nonlinear terms. And what is nonlinear terms? That is like term of the delta n to the square, or just like delta n, delta t, and stuff like that. And let's do this problem. So first, we will have the equation for nx to be n0 plus delta nx, right? And then we just need to like use the equation we found above and just put it here. And using Taylor expansion, we actually can see that the square root of tx is equal to square root of t0 times 1 plus 1/2 times delta t divided by t. And similarly, we can see that 1 over n is equal to this, right? And now we just need to plug in the equation back. So for square root of tx, we plug in this equation, which is over here, right? And for 1 over nx, that is over here. Perfect. And we need to time the whole term by this. And something to keep in mind is that the term of delta n and delta x are really, really small. But the change in delta n or the change in delta t might not be small. So that is something to consider when you do this problem. And you just need to expand out and just plug in. You will see the term becomes this, right? And now you just need to take the derivative. And you can see this whole stuff is equal to this term. And let's just take a look at each terms. You can see this one is linear. It's a linear term, right? And this one is nonlinear because there's like a square over here. And how about this? Compared to this term is really, really small. Why? Because there's like delta n over here, and we set delta n as we set this, right? Let's move on to the next term. How about the next term? You can see that this term is also like very, very small, so we can ignore this term. And how about this one? This one is not linear because of this term and times this term. Now the whole stuff will simplify to this equation. Rho EC times square root of t divided by n times the second derivative of delta n is equal to E divided by epsilon times delta n. Now we just need to equate the terms, or just move this stuff to the other side, and then like move this side to the other side, we'll get this equation over here, which is basically this. And now to solve this equation, we only need to consider this, which like most of you guys should be like very familiar with this equation, right? So now let's set lambda squared is equal to this term over here. And now you can see that delta n is equal to this. And the derivative of dn dx, or dn dx, is actually equal to this term. And why? That is because nx is actually equal to n0 plus delta n, right? And if you take the derivative of nx, you will see this term goes to 0, while this term remains. So they're basically the same. And now you just basically need to plug in the boundary condition. And from above, we can see the boundary condition. Wait, let me see, where is it? Oh, here's the boundary condition. We just need to plug in this equation. And now we'll see that sigma minus divided by epsilon is equal to this stuff. Well, sigma plus divided by epsilon is equal to this stuff. And now notice that sinh x have like this property over here, while cosh x have this property over here. So we can do some like simple cancellations and see that this term is equal to this term. So moving this and this to the other side, we'll get b is equal to this. And how about a? Similarly, we can move those two terms to the other side, and we can see that a is equal to this term. And now we just need to plug in the equations, and we can see like delta n is equal to this whole term over here. And that is question C. And now let's move on to question D, which is also a hard one. So for this question, it is assuming that the electron gas is under thermal equilibrium. So that means the force, the net force applied to the electron gas over here is basically 0. And you need to consider the pressure from the left side and the pressure from the right side. So now let's consider the volume, which has like surface area of A and width of dx. So you can see that the force applied to the right side is equal to px times A. And because electron has negative charge, and while the EX is pointing to the positive direction, this term basically is saying that the force is pointing in that direction, right? Which is equate to this whole term over here, px plus dx and times A. And now you just need to move terms, and something to keep in mind is that px plus dx minus px is equal to dpx dx times dx, right? So you'll get this term over here. And now using the equation px is equal to nxkt, we just need to take the derivative again, and we can see that this whole term is equal to this. Well, you need to plug in the equation for t, which is t0 plus delta t, and n0 plus delta n will get this whole term is equal to this, right? And now we just need to plug in the equation above, which is this term is equal to this term. And we can see that Ex is equal to this term, right? And using the method of linearization, we actually can see this Ex is equal to the term over here. Well, we set lambda square to be this term, right? And now, plugging the terms, we can see n0 k times dt divided by dx is equal to this term. Well, you just need to like take the integral for both parts and just time it by dx and take the integral. You will actually see that delta t is actually equal to delta n times this whole stuff over here and plus a constant. Well, it is important to know that from the problem, we can deduce that when delta n is equal to 0, delta t is equal to 0. So thus, the value for c is actually 0. And it will get this whole stuff over here. And this one is delta n. And now let's move on to the final question, which is just find this constant over here. So how do you do this? From the above equation, this is basically the changing potential. So we can use the equation of changing potential is equal to E dx from negative L to L, and that is equal to that term. And from this, we can see that because Ex, is equal to this part over here, right? So we just can plug in stuff and just integrate, and we can see that is equal to this term over here. And how about TL minus T negative L? We actually can use the same stuff over here. So we can just integrate and see that that is equal to this term, right? And now we just need to like divide the top by bottom, and we see that S is equal to this term. Yeah, that is question 6 of 39 CPhO, and I